So stability and balance in this section. So we're continuing with center of gravity. But if you've probably done this before, you've tried to balance things. So if you tilt a box up on one edge by a small amount and let it go, what happens?
It like tips.
It just falls right back down, right? Tilt it up a little bit more, it falls back down. Tilt it up a little bit more, falls back down, right? If you tilt it up too much, then it falls over, right? Tilt it up too much, okay, we're falling over, falling over, falling over. Falls back down if you don't tip it up enough. But if you tilt it up just right,
I don't think I've ever done that, but it'll stay where it is.
you've tried though, yeah?
But it doesn't work.
Then it will balance. So the question is, what have you found? Where does it have to be tipped in order for it to balance? What has to happen? So that's what this section is kind of about. If we have an extended object, then it will have what's called a base of support. That base of support is on which the object is resting. So if you have a box, it's resting on a base of support. So we have this box. The base of support is this right here, okay? As it rests on the table or whatever it's resting on. As you tip it up, what happens is the base of support becomes a pivot. So if I tip it up this way, then the base of support has become a pivot right here, right? As I tip it up more and more and more, the base of support length is becoming just that one single pivot, right? So now we're going to talk more and more about, or what about we're talking about is this base of support and what is happening. So if we use a car now instead of this box, we have a track width. So the car has this width W here, and now we have the center of mass over the top of that track width, and we're calling it the track width T. So we have the weight down at the center of mass. We have a torque due to gravity. So we have the pivot sitting here, kind of like the picture I drew before. As long as the center of gravity is over the base of support, the base of support is still from here to here, the pivot. Okay? As long as the center of mass is still over the base of support, the object will still fall back down to where it was before, exactly. Okay? The torque due to gravity is going to rotate the car back down to where it was in the first place. Now, what happens is the vehicle winds up eventually at the critical angle theta sub c. Theta sub c is this angle sitting right here, which is also this angle sitting right here, making with the ground. At this point, the center of gravity is directly over the top of the pivot, which is our tire that's touching the ground right here. So when we hit the center of gravity directly over the top of the pivot, that's the place where the object, whatever it is, will balance. As long as it doesn't have any motion, no speed in any kind of direction, moving it off of the pivot, if it's just sitting there, it will remain sitting there. There's no torque, no velocity moving in any direction, it stays. So this theta, this critical theta angle makes it stay. So now we have, remember we had this height of the center of gravity here. That height of the center of gravity is making that length right there. The track width in the first place had a length of t. So halfway to the center of gravity would have been t over 2. So we have this t over 2 length right here. We formed a right triangle. So we're trying to find that critical angle. In a little bit, we'll talk about that. So then once we're outside of that, immediately outside of that vertical part right there where the center of gravity was directly over the top of the pivot point, now the vehicle or whatever the object is going to tip over completely. Once we're outside of the base of support, we fall over. So that's our figure. So then in the figure above, for any vehicle, the base of support is the track width T, and the height of the center of gravity above the ground is h. The critical angle for no gravitational torque is theta sub c equals, if we look at this, we have the h on the opposite, adjacent, and the T over 2 on the opposite. So we'll use inverse tangent, and the T over 2 is the opposite over adjacent is the H. So that's why we have 1/2 T over H. And it's written like that to remind you that it's half of the track width divided by the height of the center of gravity above the ground. You could simplify that. The 1/2 would go into the bottom. And so that would be T over 2H. And if we write it like that, then you notice what has more of an impact, the height of the center of gravity or the track width?
The height.
The height of the center of gravity does. So getting your center of gravity lower is critically important for being able to handle turns or being tipped or banked or whatever as you're, like if this is a vehicle for driving. The track width is also important. It's in the numerator. So wider track width, the longer the track width is, then the better your angle is going to be. But in the denominator, the height gets doubled, so it's more impactful the higher up your center of gravity is. That's why taller vehicles flip over faster. Okay? So if the vehicle tips beyond this critical angle, it will roll over. So discuss what vehicle characteristics can impact this angle. Obviously, we just talked about it. The taller vehicle flips over faster. The vehicle with the skinnier track width flips over faster. What about what?
What about weight?
So do you see weight in this? Okay. This is simply talking about the center of gravity going over the top of the pivot, right? It does not matter what the weight of the vehicle is. It just matters where the center of gravity is. So if you load a vehicle down and that causes the center of gravity to raise, then the height has changed.
Wouldn't it cause it to lower?
It could cause it to lower, but more than likely the center of gravity was actually lower than where you loaded the vehicle down, right? Does that make sense? Like if I load up my truck, I'm loading my truck in the bed, and the center of gravity is lower than what the height of the bed is. So I actually raised the center of gravity when I loaded my vehicle. Not only that, but when I load my truck up, like here's an amazing picture of my truck.
Vroom, vroom.
I load my truck up, and the center of gravity of all of that junk that I just put in there, right, is going to be sitting up here somewhere. So I just raised the overall center of gravity of my truck. I had to have. Okay. So if you think of it that way, then, and really physically, if you've ever driven a loaded down vehicle, you know that you can't take corners as fast because you just feel the vehicle trying to roll. Okay. So this is why this formula right here is a very important formula for us for center of gravity. Okay. So a man is standing on a ladder to paint a wall, and maybe he's not standing on a ladder to paint a wall. Maybe he's just standing on a ladder to do anything, you know. He leans outside from out from the side of the ladder. If he leans too far, the ladder will tip to the side. Explain why and when the ladder will tip. What do you think?
Well, we just moved the center of gravity outside the ladder.
Yeah, so the center of gravity is definitely moving. You can see the way that they have the guy drawn in the picture here. What is he doing with his leg?
He's just lifting it out to try and balance himself.
So by balancing himself, what is he actually doing physically?
Well, when he's moving,
Yeah, he's moving the center of gravity. So if he would have kept his leg down here, his center of gravity would have already been outside of the ladder, right? So what he's doing by kicking his leg out here is he's bringing mass to the right, which is keeping his center of gravity hopefully where?
In the middle.
Not necessarily in the middle, but more importantly, within the track width of the ladder, okay? He cannot allow it to get outside of that pivot right there. If it gets outside of that pivot, what happens?
He tips.
He falls over. It's done. Okay, he's going down. So right now, that thing he's probably, because he's kicked out that foot, he's probably somewhere in this vicinity right here. If he goes much further than that, and you can feel that too. You like if you've ever been on a ladder before and you've tried to lean over as far as you could, you can feel your body's telling you, nope, you're going to go. You can start to feel when that thing just doesn't feel right. So that is a physical thing that you've learned along the way, but mathematically you probably didn't know why you were doing that. Your body is telling you you need to in order to stay up. So having somebody down here holding the ladder is helpful because now you're putting additional force down.
Which lowers the center of gravity of the whole.
It also does bring the center of gravity down, and that's going to help out a lot. So that's why having somebody help with the ladder is a great idea. But that does not help. So the ladder might not fall, but when you're up that ladder, it's not going to help you stay on because you still need to keep your center of gravity within the confines of the ladder itself. Okay. So physically, that's what's going on there. All right.
So wait, hold 1 second.
Oh,
Back up.
okay.
So will that track width change the farther he goes up that ladder?
This ladder looks like it's getting skinnier as he
Yeah.
goes. Yeah. If he's trying to keep the ladder from falling over, then the center of gravity of the whole thing needs to stay within this track width.
Okay, but
If he's trying to stay on the
The
ladder,
original one.
then his center of gravity needs to stay within the confines of where he is. And so now we're talking about this here. Okay?
but so like the farther up he goes, as it gets smaller, if he goes outside of that small area, or is
Yeah.
it still
So it's always going to be, see, he's holding over here. So that's important as well. So he's giving himself a little bit more. Plus he's throwing his leg out here. So this is actually, like if he were to let go over here and his center of gravity is outside of this base of support, he's gone, right? So because he's holding on over here, he's giving himself a little bit of an advantage. But now if he goes outside, if his center of gravity goes outside of this base of support down here, the ladder is gone. So, he's given himself an advantage here as far as not falling off the ladder, but the ladder itself is going to fall over eventually if he gets outside of the base of support of the ladder. Okay? Okay, so rank in order from least stable to most stable. The three objects shown in the figure, the positions of their centers of gravity are marked. For the centers of gravity to position like this, though, it's important to think about the fact that the objects must have a non-uniform composition. So which is the most stable, which is the least stable, and then the one in the middle is the one in the middle. We want least stable to most stable. What do you think?
I think A is the most.
I think C is the most.
Why?
Because their center of mass is lowest to the ground. Height has got more of an effect than the track line.
Yeah, but their track width is so low.
Okay.
This center of mass is so high.
The super low center of mass. What are we talking about here as far as stability?
H,
Height and,
track line.
yeah, both of those have to be accounted for, right? So really we're talking about the angle at which it would tip. Agreed?
Yeah.
Okay, so think about those two things and how they would affect the angle at which they would tip and see if that helps you figure out which one is the least stable to the most stable. So, like I said, what we need to do is look at the basically critical angle which these things will tip over. So the best thing to do is, let's say we're tipping all of these to the right, okay? So that will make a pivot on each of these right here. So the math here would work out to where if I drew an angle that is creating vertical, so I'm trying to make this vertical here, and then over through the center of gravity, and then again here, vertical, and then through the center of gravity, and then one more here, vertical, and then through the center of gravity.
You can plainly see it now.
You can clearly see, yeah. This angle right here is enormous. So this is our biggest one, right? This is our winner. And now, obviously, this one here is way smaller than this one here, right? So this is number 2 and this is number 3. So to put them in order from least stable to most stable, it goes B, A, C. You're correct. Look at the angles. Okay? So you can do it this way.
Drawing it like that.
From the pivot through the center of gravity gives you the critical angle. Okay? And that's it.